Oh, no. Yeah.
Oh, right, all right.
Oh. Come on, little laptop. You can do it.
I was going to ask, can we move the projector? Its lights are balanced.
Oop, no.
I think it's that.
Why don't you start?
Yeah.
It's okay. I mean, I don't think I have anything going on in the margin of the slide. We'll see.
Others did. It's
Overfull,
okay.
overfull H box all the way over.
Fix it. Yes, see? Thank you, man.
All right.
Yeah.
Anand, you should.
Okay. Thanks for coming to the talk. Thanks for the organizers for inviting me. I want to talk today about something hopefully maybe a little simple, but it's some work that I did with my PhD student Kostas Nikolakakis, who's now a postdoc at Yale. And I thought, oh, I'm going to a machine learning conference. I should talk about neural networks, but I don't really know anything about neural networks. So this is the neural network I'm thinking about. So there's this thing people study. There was a lovely poster yesterday on understanding functional network connectivity, which is trying to understand relationships between different regions in the brain through sensing. And people often use fMRI to do this, but fMRI measures the hemodynamic response in the brain, and it's kind of slow, and it's also expensive and loud. Who here has had an MRI? Yeah, it's like being in the worst dance club ever. So then EEG, people like to use EEG, but the number of EEG sensors in the typical the setup like Todd was showing can be not so large, but people are proposing now using high density EEG. So this is the kind of problem that's sort of motivating it. I'm not actually going to address this problem actually. So, but I just had to put neural networks in here. So what am I interested in really? We have these kind of multiple spatially correlated or sort of multiple measurements which are correlated, and that the measurements are indirect, because we're not actually measuring directly the thing that we're interested in. We're measuring it's kind of a remote sensing style problem. Remote sensing, for those who are in the younger set, was a thing that people were talking about, a long time ago. We're interested at first in the also in the correlation structure. Like we know, maybe at a first order, you don't want to know necessarily the weights between the regions, but you'd like to just know whether edges are there in the structure. So we want to look at a simple model of structure learning from corrupted data. All right, so that's the setting, and I just want to put a little fine point on it. This kind of problem appears all over the place. So I'm an electrical engineer by training. I think about devices and that they are built objects that measure things, and the data that we measure that's in your data set is actually measured with a noisy sensor. You could also think about communication constraints and quantization error, or people like interesting this robustness. We want to think about adversarial attacks, and I've worked a little bit in the past on differential privacy. So and I still work a little bit on differential privacy. So in differential privacy, as we know from yesterday, noise is deliberately introduced into the system. So there actually, I don't even have to make a case for it. The noise is there, you added it. So, right. So in this talk, I want to talk about this problem, the way we're thinking about this problem or problems like this in the framework of learning tree structured graphical models. In particular, we're looking at a hidden model problem. So like, noisy version of the problem, and try to understand what can go wrong, and then introduce a quantity that we are calling the information threshold, which sort of generalizes an object that people study when they study tree structured graphical models. All right, so let's set it up. So what is graphical model selection? For those who don't know, you have a joint distribution on p variables. You can tell if anybody was looking at Twitter yesterday, I'm displaying my affiliations by saying it's p is the number of parameters, but the number of variables in the distribution, the p-dimensional distribution, as an unknown joint distribution, and we're trying to estimate this distribution. And
P is an information theory, resonant and
yeah, I know. I've been poisoned by the statisticians. So the distribution has a factorization structure which is given by a graph, and that's why we call them graphical models. And we observe n samples from this distribution, so n p-dimensional vectors, and we'd like to estimate the graph. That's the goal. And in this case, I'm asking for something even simpler. I just want to know the graph. I don't want to know the actual conditional distributions necessarily. All right. So I was thinking about like what was the oldest paper I could find on this topic, and there's this paper by Lewis from 1959 on approximating probability distributions to reduce storage requirements, a very near and dear thing to information theorists. It was appeared in Information and Control. And the idea was to approximate some complicated joint distribution. He's like, oh no, we have n bits. N bits is way too many, or p bits. I guess p bits is very large. We can't store distributions on p bits, 2 to the p things, 2 to the p histogram. So let's try and approximate it by looking at lower order component distributions, which are just lower order marginals. He wants to conserve storage space, and but is interested in those which are particularly important in characterizing the high order distribution. And of course, we'd like it that the approximation method that you use actually do this. So he proposed a method actually based on KL divergence, although it was 1959, so they hadn't started calling it KL divergence then. It was he called it a maximizing entropy method, but it wasn't like max entropy necessarily. But anyway, he was looking to do this in KL. The problem in general is very hard. That is, the sample complexity could be exponential with respect to the degree of the underlying graph, and the computational complexity can be NP hard. And so I don't like hard problems. I like easy problems. So I'm going to stick with the tree. I'm going to assume that it's a tree, like the simplest graph I can think of. Even forests are harder than trees. So let's stick with a tree. So the distribution of X is non-degenerate and factorizes according to a tree. And this tree is connected. So it's a tree, not a forest. And we're going to assume that the mutual information between is positive for all the pairwise variables. And I'd like to note that trees are still useful. I mean, it's not. I'm not doing this just because I'm lazy. It's because trees are actually still also interesting to try and approximate. Also, I can say something, so it's good. So the classical algorithm for estimating trees, yeah.
What's the difference between the second and the third section?
I think that they're the same. Yeah. Sorry.
So is your the neural network you started with a tree-like?
No. That's why I just had to put that in as a joke about neural networks at the start of the talk. Forget about it.
Sorry.
Called me out. Okay, classical algorithm for this is due to Chow and Liu, which was published in the IT Transactions in 1968. So happy 55th birthday to this paper. We should have a cake later. And it's very straightforward. You compute the empirical distribution on all pairwise variables on every potential edge, and then you plug that in to compute a plug-in estimate of the mutual information between every pair of variables, and then outweight the maximum weight spanning tree. And this is like a pretty natural thing that you would think about doing. And in fact, it turns out to be a pretty good idea. So cheers to them, having brought us this lovely algorithm. So it's a pretty good idea overall, I would say, Chow Liu. It is in fact the ML estimate of the factorization structure. So this is, we like maximum likelihood. It's a consistent estimator. In this lovely work from like 12 years ago, would show that do some error exponent analysis for those who are really hardcore information theorists. As we all know, these are hardcore information theorists. Extension, and you can, if you want to do forests, because you're like, Anand, you're too lazy, you should do forests. It's already, hey, Vincent has done it for us. So there's extensions to forests. It's also a good idea there. It has an optimal sample complexity for this learning to make predictions problems, or if I want to predict one subset of variables from another subset of variables. So this is more recent work by Bresler and Karzan, which is actually what sort of inspired us to think about this kind of problem. And it can also be used in other algorithms. So you can use it as a piece, like Chow Liu might not be itself the thing to do, but you could use it as part of a more sophisticated algorithm. So this a nice paper from last year, which calls it CL++, Chow Liu++, that can handle things like model misspecification. But that last point kind of raises an issue that's not like the best thing to do all the time. Like it's not always the best thing to do. So you need other ideas. There are other ideas out there for estimating this tree. Interaction screening or the sparsitron are also very good ways of estimating sparse graphical models. And if you're not quite in the plain situation that I mentioned before with this tree structured model, like if you have noise, or if you have outliers, or if you're actually not sampling from a distribution but close by to a tree distribution, or somebody has corrupted some of your samples adversarially, or if you have a different type of model misspecification, you're close to a tree, but again, in a different sense. In all of these cases, you need something more fancy than Xiaolu. But I like to take it old school, so I'm going to stick with Xiaolu, and I want to know what can we say about Xiaolu in this context of noise. So, and the reason I want to do this is I want to emphasize a sort of meta point, which is that the modeling assumptions that we make have some semantic value, and so that when we decide to set up a model for our problem, we should think about what does it mean. So I might be trying to distinguish which tree I have, right? So noise, a noisy model could say like, well, it's a tree, but has some junk on it. So let's like try and recover the tree. That's a straightforward one way of doing it. On the other hand, if I think about adversarial perturbation, I could say that most of my data actually comes from a tree, but some of it's been poisoned. Some of the samples actually come from broccoli. And so you want to get rid of the broccoli. And then you want to then keep the tree, get rid of the broccoli. But you could say also close to a tree could be like the real data is actually broccoli, which looks like a tree. So what is the closest tree that looks like broccoli? And I'd argue it's the top left one. So that's a different, again, these are all kind of different ways of actually trying to say what it is that what's the relationship between the real world and the measurements that you're making. And then, of course, you could have sort of robust statistics or thing about rejecting outliers is most of my data comes from the tree, but actually some of it comes from something completely different. I don't even know what it is. That's the Huber-style robust statistics model. A percentage of it comes from some other distribution like sloths. And then we want to, again, get rid of the sloths. Sloths are not pretending to be trees, whereas the broccoli is kind of pretending to be a tree. So these are kind of also different assumptions that you're making. So we don't often get to measure X directly. And so we're going to consider a hidden structure problem. So instead of the X's, we're going to measure Y's. Y's are corrupted versions of the X's. But the hidden model is still a tree. So we're going to assume that the underlying reality is that things are related to by a tree. And what we want to estimate, what we get to measure are the Y's, and then we want to estimate the X's again. So that's sort of straightforward. So the problem is then, if on the face of it, maybe you don't know what the structure is, but then given n observations of the Y, how can you estimate T? And in particular, the question we're interested in is what is the impact of the channel or the relationship between X and Y on the number of samples that you need to estimate T from Y versus the number of samples you need to estimate T from X. Yeah.
You know the P of Y given X model or no?
At the moment, we do. We're trying to characterize what is the impact. We're interested in we don't need it for the estimator, but we do need it to understand what the bounds are going to be, like to pick the sample complexity. But we're interested in the question of what is the impact of that channel on the estimation. So, for example, is it worth spending another $100 to buy better sensors with higher SNR? So that would be a kind of question that would be motivating this. Any other questions at this point? Okay, good. So the work on the noisy data problem is a bit more recent than the work on the than sort of classical child use so on. So we did some work on easing model trees, which are just binary with binary variables and IID binary noise. So we pass every bit, we have correlated bits, and the joint distribution factorizes according to a tree. We put that vector through a memoryless binary symmetric channel, and that's what we get to observe. We flip some of the bits. People have looked at kind of around the same time. This group was looking at erasure channels, and I think erasure channels are really important to look at because in almost any real application, you talk to statisticians, there's always missing data, and we always just assume we've already filled it in often. So like missing data is actually very interesting to think about, I think. If the noise isn't IID, that is, if the noise, both of the noise is dependent across variables and and or it has a different distribution at each node, then sometimes you can show that in some examples and I'll show one later that the Chow-Liu algorithm will fail. That is the but if you know those differences, you can sometimes correct for it. But there are other algorithms which could work in this setting where you have different say bit flips on every variable. You can get a fancier algorithm if you're interested in error exponents, but they kind of restricted to Ising models. So all these results are basically on underlying binary data, and then the x's are binary, and you're putting them through some binary input channel. With the exception of this work, which talks about a connection between running Chow-Liu with this continuous corruption model. I think they're motivated by a problem in genetics, phylogenetics. Okay, so what we're interested in actually is what happens when the x's are not binary. So we want to think about the general alphabets for the x's. And because, although as information theorists, I think that I should be able to understand everything through binary or Gaussian examples. There are in fact other things to think about than binary and Gaussian examples, but and we want to understand what makes a particular model, in particular, what makes a particular noise model easier or harder to make the problem easier or harder from an estimation perspective. All right. So let's look at this hidden tree with discrete alphabet. So I'll just set up the model again. We have p variables with an unknown tree structure. Each xi is going to be in some discrete alphabet. We're actually interested in both finite alphabet and countable alphabets. For a reason, I'll give an example in a minute. If they're countable, we have to make some assumption, and an assumption that we're going to have to make, if anyone is familiar with this entropy estimation paper by Antos and Contillanes, if not, you should read it. It's a really nice paper. We need to be able to estimate information quantities successfully. So we need to make some assumption about how small the probabilities can get, how fast the probabilities can decay in the for the distribution on x's, and so this is the assumption we're going to have to make. So again, we have this connected tree, and the observations are generated by passing each xi through an independent and, in this case, identical discrete memoryless channel, and each yi is going to take also values in a possibly countable alphabet. So this is I think now I've saved the model 3 times, so hopefully everybody's on the same page. So there are a lot of examples of this. Obviously, the one I said before, which is like a binary data, and then you flip some of the bits of the binary data. You can also think about categorical variables corrupted by randomized response. This is the kind of situation, maybe from a differential privacy perspective, that I'd be interested in. And then, of course, there's another example, which I think is pretty interesting, which is that each variable is Poisson. You're measuring some Poisson number of arrivals, and you have what you can measure actually is only a thin version. So underlyingly, there's like xi photons coming in, and you can only measure yi photons. And so I think this is pretty interesting. There might be some connections like Hawk's processes and stuff like that, but I did need. You could. I would just as an example of like a thing you could try to do.
Well, photon counting devices don't add noise.
They could make up make a hallucinatory photon
Maybe
detector.
drop photons, but they not register photons, but they never.
I was trying to get a thin pufferfish, but I couldn't manage to make that work. So what we want to do is see what can we do with Chow-Liu, and in fact, is Chow-Liu a good idea in this setting? Because Chow-Liu was a good idea actually in the binary case. So again, this nice paper by Antos and Contillanes kind of analyzed the plug-in estimators for entropy. These estimators have some bias, so there's something you have to deal with in the estimation. And in the binary case, you can identify the source of error in the Chow-Liu algorithm. That is, when does the Chow-Liu algorithm fail? It fails precisely when you have a particular kind of data processing inequality, what I think of as a data processing inequality violation. And so we can sort of generalize the whole point. The main point of this talk is you can generalize this condition in the noisy case as well. So what can go wrong? So remember, the Child-Liu algorithm is compute the pairwise distribution on every edge, and then find plug-in estimates of the mutual information, and then output the maximum weight spanning tree. So if we do that, the problem is the Markov random field. If I think about the distribution on the y's, the Markov random field is a complete graph. So if I wanted to think about, Child-Liu on the face of it should not work in that setting, because in fact, your underlying model, if I think about the y's, it's not a tree, it's a complete graph. So that's why Child-Liu can become an inconsistent estimator. But if you look at this very simple example where you have kind of three variables, where you have a weak connection between x1 and x2, but a strong correlation between x2 and x3, and then you have different noise levels on each one, then if you have a situation where the mutual information between y1 and y2, or the y1 and y3 is actually bigger than the mutual information between y2 and y3, then you're going to end up constructing a tree which doesn't get that edge between y2 and y3. So and if you say, and you're like, okay, well that when does that happen? And you chug through, and everything boils down to the correlation coefficient for the binary case. So you just get this condition on the relationship between these noise levels, that if there's some sort of threshold on the correlation, if this inequality is violated, then Child-Liu is bad or doesn't work. So one approach is, of course, to just throw up your hands and give up. But these guys have been around for 55 years, so I want to keep working with them. But you can use it. So you can use it in a more complex algorithm. And what we observed actually in these binary settings is that if you do know something about the noise model, you can do some pre-processing, and this will create a make Child-Liu consistent again. So this is the sort of setting on the binary case. And so the question is, do we have similar setting in the general case? So here's where I want to introduce this information threshold. So when does Child-Liu make mistakes? So basically, we want to look at triples of basically an edge in a path, a path with two endpoints and an edge in the middle. And so what you can show is that the Child-Liu estimator is not consistent if you can find a path and the edge in the middle such that the mutual information on that edge, which should exist in the graph, is in fact smaller than the mutual information between the two endpoints of the path. So what will happen is those two will get connected in this path. In this path, W and W bar here will not get connected, but the endpoints will get connected. But they should be connected. So that's what's going on. And so if you rearrange this and you look at in the noiseless case, you can just sort of say, oh, okay, well, what if I just look over all paths and I try to find this minimum or this gap here between the mutual information on a link, the weakest link, if you like, and the endpoints. So if this gap is strictly positive in the noiseless case, then in fact the error probability for the Child-Liu algorithm decays exponentially. This is a result from Khan et al. And so we interpreted this as an information threshold and asked, in the noisy case, is it in fact the same situation? And here we always have that this quantity is positive because of the data processing inequality. Whereas in the noisy case, it's not necessarily the case. So if we just replace x's with y's, we can define an information threshold here. But this can be negative. And in the case where this is negative, you can show that Child-Liu will fail. But if you could look at the condition, whether it's positive or negative, you can generalize this Ising model thing that I showed before with its correlations. You can generalize this condition to non-parametric models. And so then the question is, well, if this thing is positive, like how does this thing relate to the number of samples we're going to need? And in particular, if you can do some pre-processing, for example, to make the pre-processed version or post-processed version, they post-process the data, you can force this thing to be positive, then you can show that Child-Liu will work on the post-processed data. So here's a result. So if we fix a class of underlying models for X, and then we have some parameterized family of noise variables, then we can find a constant such that the sample complexity is like log p, which is what you want. The delta is the failure probability, but it's 1 over the information threshold squared. And so this holds for when this information threshold is positive, and this quantity is a function of the distributions of the y's. We have a converse, which basically says that unless you have, if you look at a class of models for which the information threshold is bounded away from 0, then that bound, if you don't have enough 1 over that information threshold squared number of samples, your estimator will not work. So this is the minimax lower bound. So our contention is that this noisy information threshold actually is characterizing the sample complexity. It's a function of the noise distribution. So what's good and bad about this? So the good part is that we can, we have a quantity which says whether or not whether the estimation problem is this is over all estimators. So this says that child U is optimal for this class of models with positive information threshold. The bad part is, of course, that the constant C in the upper bound is going to depend on the underlying class of models. So it's not like independent of the underlying model and the noise. So we need to do some more investigating here. And of course, then the hidden thing is like, how do I actually calculate this quantity? And so I'm going to dodge the bullet on that one and say, I don't know. So in fact, I will leave that for future work. So we can compute this quantity in some simple cases, like in the binary case that I showed before. And one question we've been asking ourselves, had been asking ourselves, if we can understand the relationship between the noiseless information threshold, the noisy information threshold, maybe using some SDPI sort of stuff. And how can you estimate this threshold? And what are the implications for privacy? We haven't really thought about that yet, yet. So I think that's all I have to talk about. So thank you very much.
Questions from? Yeah, no question. Suppose I know the structure of the memorless channel P of Y given X. Suppose I didn't want to constrain myself to child loop. I wanted to search for the best tree distribution, and all I'm given are the Y's. But I know the P of Y given X. Have someone thought about formulating that problem and what the structure of that
I mean, the best tree approximation to the underlying distribution.
the underlying joint distribution?
So the stuff that I presented, the references on like model mismatch, those are saying, oh, you're close, your distribution isn't a tree, but it's close to a tree, which is a little bit different than saying your distribution might be far from a tree, but if you want a tree, this is the best tree you can get. That's a different, not sure actually off the top of my head if that's there, but there you would probably want to use a different estimator. I think.
If he called his question stupid, this is terribly stupid, but this
I think
one
that's
work
stupid
by
answers.
Karmanis and these other guys
Yeah,
on robust tree selection.
that one of the references was.
Okay, yeah, so how does that relate to this?
Okay, so it depends on the model. I can't remember exactly which one, which model it was, but it's one of these other noise models where you're actually, so some of them, I can't remember if that one is one of the ones where it's the data set, the samples are poison. So some of the samples, like a robust statistic, some of the samples come from another distribution, or it's one of the ones where it's close. You're sampling your distribution is close to a tree within total variation distance, and then you want to. I'm sorry,
No, I also don't,
I don't
we have
remember
a
which
paper
one.
on this and I don't
Yeah.
remember myself, so.
I'm not sure, by the way, I enjoyed the talk, but I had one question. You mentioned the Kantoyanis result. So, but as a follow-on to that, there was that thread of work with like Yihang Wu and Zhao Weissman and so on estimating
Yep.
in a couple of ways. And kind of you plugged into this.
Yeah. I think actually I would say that. Yeah, so I would, yeah. So we, I think when we went through the argument, it turned out that the entropy estimation is not the problem. So like getting a better entropy estimator isn't going to meaningfully change. But we should do that. we should use the best entropy estimator we can use. But because we're basically we're not digging into the estimator. They're not exploiting anything particular about it.
I have a question. Yeah, you mentioned adversaries.
Yeah.
So if each channel is an APC or something, like, do you think some version of this would work
Well, I don't think if each version is an ABC
with cost constraints?
with cost constraint. That is a very interesting question. So for those who don't know, an ABC is an arbitrarily varying channel. It is a channel that states that is controlled by an adversary, and the cost constraint you're saying, like, for example, in every sample you could flip at most a fraction p of, or we have p, so you could flip at most a fraction q of the bits in each sample, but if that's done in an adversarial way, can you then say something? Well, I think the thing is that some kind of adversary like that might be able to just delete a whole section of the graph. So then I think it would raise very different, but also interesting questions about what you can see when somebody can target the erasures might be easier to think about.